this water I just drank isn't radioactive.
You're not dead.
True is. You don't know. So radiation is tasteless, odorless, colourless. It doesn't fizz, doesn't glow green, and it definitely doesn't politely announce itself before it ruins your day. So, looking for radioactive material in water is a little bit like hunting for an invisible squid. You might know it's there, but you can't directly see it. So you have to make the little rascal reveal itself. Now, how do we do that with radiation? Well, that's where radiation detectors come into it. So they reveal the invisible to us, and they do this by converting something you can't see into something you can measure. So, now this mysterious liquid here isn't radioactive. It's much worse, it's tonic water. But you can see, it glows under UV light. So what's happening here is there's quinine inside the tonic water, which absorbs the UV rays, and it releases this sort of visible blue light. So that's one of the ways that detectors can help us see the invisible and turn radiation into light. I've got another example here. So can you guys see that? Kind of, not really. It would be really hard for you guys at the back too. How about now? Yeah. So this here is a scintillating crystal, and it's the one that I'm using in the detector field called SQUID, which stands for Strontium-90 Quantification and Underwater Isotope Detector. So what I'm doing is I'm basically building a detector that will hopefully sit in some water and look for Strontium-90 contamination. Or even a Strontium-90. For starters, it's completely man-made. It was practically non-existent in nature until the 1940s when we first started testing nuclear weapons and eventually generating nuclear power. Now, the awkward thing about Strontium-90 is it sits directly below calcium in the periodic table and chemically behaves quite similarly to it too. So that's important because calcium is used to make what in your body? What is it?
Bones.
Bones, yep. So in this water that I drank earlier, if there was some Strontium-90 floating about in there, my body would have mistaken it for calcium and deposited it into my bones and teeth. And once it's there, it continues producing radiation, which increases the chance of bone cancer and leukemia. Yikes. It's also really soluble in water, and it has a half-life of about 29 years, which means it sticks around for a while. So radioactive water, one example of why radioactive water matters is in Fukushima. So after the accident in 2011, water became one of the hardest parts of the cleanup. You needed water to cool down the damaged reactors, and of course that water then became contaminated. And on top of that, you had groundwater, which was constantly flowing into the site, which also added to the problem. So since then, a huge amount of water has been collected, treated, stored, tested, and managed really carefully. Now, this case was discussed publicly quite a lot because of tritium, so that's another radioactive isotope. But the lesson here is once you have radioactive material in water, dealing with it becomes really slow, really expensive, and potentially politically explosive. So a little bit closer to home, over at Sellafield, there was a Strontium-90 leak reported, and that Strontium-90 has managed to contaminate the groundwater beneath the site. Ooh. So what they do at the moment to monitor it is they take water from the ground and they transport it to a lab that's off-site to find out what's in it. And this whole process takes quite a while, it costs a lot, and it even produces secondary waste. So my alternative solution is we deploy SQUID. So SQUID will hopefully just sit in the water, directly in the groundwater, and kind of give you useful information in real time. So how does SQUID work? Well, Strontium-90 emits beta radiation, which is fast-moving electrons. Now, these electrons interact with that beautiful orange crystal I showed you before, and they deposit their energy into it. And this energy is converted into photons, which is shown by the little sparkles on the animation there. So that's great. We've turned the invisible, the electrons, into something visible, the photons. But now we need something to count those photons, which will tell us how much radiation you have, and you also need to know the energy of the photons, which tells us what kind of radiation you have. And for this, I'm using a silicon photon multiplier. So that's the smaller rectangle you see there. And what that does, it's an incredibly sensitive light sensor. It collects those photons and converts them into an electrical pulse. And these pulses can be counted. And also the size of the pulse is proportional to the energy of the original beta particle which hit the crystal. So that's how squid works. And the main goal of squid is, instead of taking the water to a detector, why not put detector in water, right? Amongst that, I also have to make sure it works really well. I have to constantly take it apart and put it back together, run experiments and simulations, occasionally blow up some electrical components and question my sanity, but sometimes I'm allowed outside and I get to talk to lovely people like you. And I really hope that you've learned something new about radiation and detectors tonight. Thank you, and good night.